So again, the process has this raising and decreasing prices that makes us worried about possibly cycling. In order to prove that this will ever end, it would be best to find some kind of quantity that goes in one direction. Prices go up and down, and that makes it harder to argue with them. We're going to think of something that I'm going to call potential energy of the system, an energy that keeps going lower and lower and lower. As we go, it always decreases. And if we find such an energy, that's a good argument that the process has to end. Energy can't get arbitrarily negative. So the way we're going to think of this energy is the expected or hoped for benefit of all participants. That's going to serve as our energy function. So energy will consist of two parts, just the same way as the matching value consists of two parts. The sum of current prices is going to be the part that the sellers hope to get. Each of them are hoping to get whatever the current price is. When we raise the prices, they can hope for more. When we lower the prices, they have to be accepting lesser prices. And then we add to this the maximum net values for the buyers. So for each buyer, we look at what's his or her current favorite item, the one with maximum net value, and sum those up. This is not a matching because they might actually have a conflict and might want the same item as their favorite item. But for each buyer separately, this is the maximum value they're currently hoping for. And that's what I'm going to add up in the energy function. So again, the energy consists of sum of current prices plus the sum of maximum net values of all the buyers. Energy, of course, is always non-negative. The prices will stay non-negative. Everyone hopes for a non-negative net benefit when they buy an item. It's going to start very high. At least all the buyers will hope for the very best item at all of high value. And we're going to argue that it decreases in every iteration. If the values for items are all integers, it's going to decrease by at least 1 in every iteration, which then will imply that the iterations have to stop. And recall, if the algorithm ever stops, those are market clearing prices, and the resulting matching has maximum total value. Okay, so we need to think about what are the situations in which this energy changes. Energy is determined by the prices. In one hand, because that's what the sellers hope to get, and the other side, because the net values depend on the prices. So there are two things we might be doing with the prices. Sometimes we increase them, and sometimes we decrease them. So let's start by thinking about the effect on the energy when we're increasing prices. So when we're increasing prices, we find an over-demanded set. So we find a subset S, a constricted set in the preferred seller graph, where if I connect each member of S with the item they prefer, that results in a neighbor set of S that's actually smaller than S itself. And what we did is increase prices on this neighbor set. And we're wondering what the effect of this on the energy. So on one hand, this looks like it increases the energy. We increase the prices on the neighbor set of S, so the sellers now hoping for 1 extra unit of money as their price went up. But at the same time, the net values on the S set, the set that had the constricted, or the constricted set that had the over-demanded desires, will decrease by 1. These were their favorite items, and every one of them went up in price by 1. So the net values went down by 1. And every other net value was already 1 smaller. So here we have a set S whose contribution to energy decreased by 1 each, and the set N of S whose contribution to the energy increased by 1 each. And because S was a constricted set, S is bigger than the neighbor set, so in total, the energy decreased by at least 1, by at least the difference between S and the set of neighbors. So indeed, as we hoped for, the energy, when we increase the prices, must go down at least by 1. Okay, so this worked out well when we're increasing prices. We need to think about the effect of decreasing prices. So remember, we were decreasing prices when all the prices were positive, and we simply subtracted 1 from every single price. When this happens, then the price for all the sellers goes down by 1, so their contribution to the energy goes down by 1. Every single one of them loses 1 from their price. But prices now have a positive effect on the buyers. The net values that they hope to get now goes up by 1. Every price went down by 1, the values didn't change, so the net values, every single net value, went up by 1. It didn't actually change the preferred buyer-seller graph. The preferences stayed the same, but the values went up by 1. So the seller's values went down by 1, the buyer's values went up by 1. In our setup, we have the same number of sellers and buyers. So again, it turns out the energy in this case didn't change at all. So to summarize, our algorithm had 2 kinds of steps: the increasing prices that turn out to decrease the energy, and decreasing prices that turn out not to affect the energy at all. So every cycle of iteration, we're decreasing the energy at least once, and we're never increasing it, which then shows that market clearing prices must exist. This process must need to stop, and it can only stop in market clearing prices.